So really excited to have him later on. But before Matt joins us, let's introduce our co-stars. First, PhD candidate in astrophysics from the University of Chicago and host of her own YouTube show, Nora's Guide to the Galaxy. It's Nora Bailey. Hey, Nora.
Hi, everyone.
Next, Deputy Director of Education and Public Outreach at the Vera Rubin Observatory. It's Dr. Lauren Corlees.
Hello, happy to be here.
Hey, Lauren, thanks for joining us. Next, medical doctor and founder of Orbital Biodesign, it's Dr. Danny Carroll.
Hey, everybody, good to be here.
Hey, Danny, thanks for joining us. And last, but certainly not least, postdoctoral scholar from the Simons Observatory, it's Dr. Nick Galitsky.
Hi, everybody.
Hey, Nick. Well, so lovely to see you all again. We are going to try doing things a little bit different on the Cosmos Show this evening. We're going to jump right in to Astro Advice, and then we've got a new segment after that called Astro 365, where we'll talk about some events that happened on this day in astronomical space exploration history and during the first couple of weeks of December, since we just do this show every 2 weeks. And just a reminder to our audience before we go any farther that you can chat your comments on Twitch and YouTube, and you can also call us and speak with us directly by calling a number that you see on your screen and using the meeting ID in that YouTube, excuse me, not YouTube, but Zoom window. So anyways, getting back to life advice from astronomers, Astro Advice. Tonight, we're going to be talking about the James Webb Space Telescope, one of NASA's largest and most powerful telescopes ever constructed. And hopefully it's going to see the first light in the universe, which Dr. Greenhouse will tell you all about later. But such a revolutionary next step in the history of astronomy deserves some revolutionary comment from a former astronomer who really changed the way we see the universe. And so the astronomer that we have in mind for tonight is Dr. Vera Rubin, who was a pioneering figure in the research of galaxy rotation rates, which eventually led to the discovery of dark matter. And Dr. Rubin says, each one of you can change the world, for you are made of star stuff and are connected to the universe. And I love that quotation for lots and lots of reasons. But I've already been rambling on for a while now. I'd love to hear what some of the co-stars have to say about that, or anything else on your minds astronomically related.
Yeah, this is, I think, a really inspiring quote. It's a little cheesy, but
definitely high in the cheese factor. Yep.
And this is not necessarily in the quote, but one thing that I think is really interesting about Vera Rubin's career is that earlier on in her career, she was actually working on something, and I forget the details of it, but it was a little bit controversial, and she didn't really like that. It wasn't very enjoyable. So she pivoted to doing these rotation curves, which were kind of a straightforward thing that she was just going to go out and measure. And then, well, bam, dark matter. And she totally changed the world. And she was kind of actually trying not to be. And she ended up being this just like really pioneering scientist. And I just think that's really inspiring. And she's very awesome.
Yeah, I actually wonder whether or not that story is actually behind this quotation. That first part of each one of you can change the world. The fact that she did end up doing this, mundane graduate research project and ended up being revolutionary. I wonder if that's where that came from. And Lauren, I wonder if you know whether or not that's where that came from, since you do work at the Vera Rubin Observatory.
It's true. I'm not sure if that's exactly what she meant when she said this, but what it also reminds me of is a lot of the work that she did to also promote women and other people to participate in science. And so I think when she said in this quote, each one of you, she really meant like each and every one of you has the possibility to participate in science in this way. And that's definitely a part of her career that I'm really inspired by as well.
Yeah, thank you for mentioning that.
Yeah.
That's fantastic. Wyoming Stargazing is actually in the process of launching a diversity in STEM scholarship fund in order to support women and all other underrepresented youth in the STEM fields. So we're really hoping to do what we can to get people inspired to study not just astronomy, but all the sciences. Yeah, I mean, one of the reasons we do the Cosmos show is to do that. So thanks for helping us do that already. Nick, it looked like you had something you were going to say.
Always back on a different topic,
so
but
thanks for helping us do that already.
This kind of quote I was thinking about it, the whole made of star stuff thing and how we kind of figured that out. And reflecting on, we're probably one of the first generations who knows the journey of, to some degree at least, of how the atoms that comprise us got here. Although with a few dark ages and what have you to figure out still, but to tie it back into JWST.
Yeah, I mean, I thought that was kind of an interesting connection as well. I mean, and I have the really fascinating thing about all that is like, that's really just happened like in the last 100 years. You know, we've gone from Hubble, making some discoveries that really show that even other galaxies existed, that the universe was as huge as we know it is today, to starting to understand some of the origins of the universe and hopefully learn a lot more with the James Webb Space Telescope.
So just to add on to this, not to take it in a morbid direction or anything like that, but the physician in me sees a quote like this and thinks about our own mortality and how it really is life is kind of a limited time thing, and that it's going to be somebody else's turn pretty soon, in that connectedness to the universe piece. So I don't know, I find it motivational to think like that, almost like stoic along those lines, but anyway, I think it's a great quote regardless. So
yeah, I mean, everything's always changing, right? We do have just a short time on this world, and yeah, the stuff that makes up our bodies eventually gets recycled into something else. I guess since you mentioned that, Danny, I'll mention something that I just heard about on NPR the other day, which maybe also is a little morbid, but connected. Apparently, there are now 2 states in the country where you can get composted. You can have your body composted as opposed to buried or cremated or buried at sea. So yeah, a little bit more a way of thinking about how we might become interconnected with everything else. I kind of like the idea of being part of someone's garden someday.
That's interesting.
Well, it's like getting the diamond made, right? If you're like, which is, diamonds are just carbon, and I mean, carbon is really one of these things that does come from the stars. So full circle.
Totally. I actually think that's why we're so attracted to shiny things. I think it's because humans have been looking up at the sky for the last couple million years and at the twinkling stars. I think that's why diamonds are a thing. Danny, do you have something else?
No, I don't think so.
Going after the tough questions here, would you rather be composted or launched into space after you die?
Or are we talking like we're talking like cryogenic launch into space,
No,
but
potentially
potentially being revived?
Services, I think it's just your ash, right, or something like that.
Like jettisoned into space.
Do you like become like a shooting star? Is that the point of it? That would be neat.
That'd be kind of fun.
I mean,
it'd be a lot more useful as compost, but it's not quite as poetic.
That's fair.
No. I mean, as long as we're talking like 100% vaporization as a shooting star, I would not want to become space junk. So as long as we're talking like fully burned up in the atmosphere, I am good with that. I mean, I could totally see somebody trying to do that as another way to do burials. Like that would be like almost like a sky burial, but way higher up in the sky.
Emerging market. Let's get some seed funding and go for it.
I mean, no, I mean, I would be shocked if there isn't a company already thinking about selling this, right? I mean, yeah, if we can like, have a space tourism industry launching people into space for a few minutes, why not launch a little like, human dehydrated, pellet into space and have it burn up in the atmosphere? Like, I don't know, Nick, if you don't do it, I might.
That sounds like fun.
Fun is not the word I would use for that, but okay.
I don't know, but I think I would much rather end up in somebody's, garden or as a shooting star than to have, like my last event as a human be, cremated, like producing CO2 gas. I'd much rather go that way. I could see burial at sea as well.
You can't actually be buried at sea without being cremated first. You're not allowed to just dump bodies.
Oh, that's a bummer.
I know.
Okay,
This one I was in the Navy and it was very disappointing to me.
Oh, yeah.
Really? I would have thought international waters,
Maybe, but I think there's still like guidelines over what you're allowed to dump into the ocean.
Oh, that seals the deal for me then. I definitely do not want a burial at sea. So yeah, compost me or shoot me through the atmosphere and watch me go as a shooting star. I kind of love that, actually. I'm actually going to do a Google search on that after we're done tonight and see if anybody is doing that. I think it's actually a really good idea.
Call up Elon.
Right? All right. So I think there are even more connections between this quotation by Vera Rubin than what we've made light of already. And part of it ties into some of the stuff that actually came up in the history of astronomy for these first couple of weeks of December. So let's move down to that. So actually on December 7th, what I found was that the Galileo spacecraft actually arrived at Jupiter in 1995. And as some of you probably know, the Galileo spacecraft was responsible for several monumental discoveries about the solar system, including that there was probably a saltwater ocean under the ice in one of Jupiter's moons, Europa. That two of other of Jupiter's moons probably also had saltwater oceans on them. Somebody just chatted in that they want to be buried on Mars next to Elon. Nice. I don't know if Elon is bold enough to take that first step like Bezos and Branson did. I think he will not be the first person to go up on one of his rockets, but I could be wrong. We'll see.
I feel like on Mars you would like almost need to be composting the bodies. I don't know that they have the luxury of just burying them.
Yeah, I mean, I don't think there are any living like soil microbes though in the Martian soil. So I don't think your body would break down, would it?
No, you'd have to bring some along. I mean, that's precious organic material.
Sure. I mean, I guess if like you don't have a lot of like dehydrated human feces to compost with, as the guy did in The Martian, then you can use human bodies. All right, now we've really gone down to a dark place. All right, let's bring it back here. Sorry for all the kids who are watching this. We're all upstanding citizens here, we promise. So that was actually today on December 7th, 1995. Lots of other really, really interesting things in the first couple of weeks in December in the history of astronomy. December 1st was the night or day, rather, I'm not sure, that Sputnik 1 actually re-entered Earth's atmosphere. The very first satellite ever launched from Earth. It was launched, I think, on October 4th of 1957. But then just under 2 months later, decayed back into the atmosphere and burnt up. Which is pretty cool. It was December 6th that the US tried to launch their first satellite, 5 days after the Russian satellite burned up in the Earth's atmosphere. That was a failure, unfortunately. That was the Vanguard TV3 rocket. And I think it was almost another year before the US was finally successful in launching their first rocket, Explorer 1, if I'm remembering correctly.
I believe it was in March.
Okay.
So just a few months.
Few months. Yeah. So yeah, some interesting rocket history. And then there are a couple of really cool birthdays in the first couple of weeks of December in astronomical history. Annie Jump Cannon was born on December 11th, 1863. Another amazing woman in the history of astronomy. She pioneered stellar classification using stellar spectra, and specifically classified stars by their temperature, and developed what is today known as the Harvard catalog of stellar classification, which has morphed over the years. We now use something called the Hertzsprung-Russell diagram, but her work was pivotal in helping us classify stars in really the modern way that we still do. So that's Annie Jump Cannon, an American astronomer, by the way. And then another interesting birthday in the history of astronomy this month is Tycho Brahe, who was well known in astronomical circles for other reasons, some really bizarre and interesting ones, actually. Some of you astronomy buffs already know that he lost part of his nose in a duel with, I think it was one of his cousins, actually, and wore a prosthetic nose for the latter part of his life. There are some stories that say the prosthetic was gold. I've seen brass also as one of the materials used, but it sounds like he did have some kind of a metal nose after he lost part of it in that duel. But astronomically, he made some really amazing data collection efforts in looking at the motion of Mars and other planets. And it was his data that Johannes Kepler eventually used to figure out his laws of planetary motion. Apparently, when Kepler was working for Brahe, Brahe knew that he was a better mathematician and probably would figure out the stuff that Brahe couldn't figure out, so kept his data secret from Kepler. So it was only after Brahe's death that Johannes Kepler got a hold of his data and figured that stuff out. So interesting stuff there. I should also mention that this has nothing to do with astronomy, but it's also my grandmother's 94th birthday this month as well in just a few days. So happy birthday, Grandma. All right, I'm rattling on a lot. I'm sure that the co-stars have some interesting things to say about all this stuff that we've been talking about. So love to hear what's on all of your minds about any of this stuff that I've been rattling on about.
Well, this isn't strictly astronomy, but when I think Tycho now, I think of the Tycho space station from The Expanse. We all have that to look forward to if we become famous astronomers. And also one of the, or maybe even the most noticeable features on the moon is the Tycho crater. So
totally.
Pretty cool. I think that's a fun one to like spot once you realize, because it has very long, I don't remember what the name for it is.
Ejecta lines.
Ejecta lines. So you really kind of brings forth an image of like something really smacked into the moon.
Yeah, it's incredible. And you know, it's one of the things that we show most of our guests on stargazing programs when the moon's out. So these ejecta lines that Nora was just talking about, they go like a third of the way across the surface of the moon. So whatever it was that smashed into the moon to create this crater had so much energy that it shot rocks, moon rocks, out of this hole that it created a third of the way across the lunar surface. And you can still see those ejecta lines. They look like kind of radial lines or like spokes from a wheel coming out of this crater on the moon's surface. And they're so well preserved from hundreds of millions of years ago because unlike on the Earth's surface, there's no wind and water erosion. There's no atmosphere at all. There's no mountain building, volcanism. And so the lunar surface stays pretty much the same as it has for at least a couple 100 million years. I can't remember the latest estimate on when the last time there was an active lunar surface. Do any of you know that by chance?
I remember that the samples China just brought back from the moon were a couple billion years younger than any of the previous samples, showing signs of more recent volcanism. But even that, I think they're like 2 billion years old. So, but I think the samples that had previously been brought back were like 4 million or 4 billion years ago. But yeah.
A ways back. Any other thoughts or meanderings about any of that stuff from astronomy, history, or how it relates to current stuff? All right, well, that'll be Astro 365 for today. So every couple of weeks, we'll bring in some more cool facts about the history of astronomy, and yeah, we'll chat about it. All right. Well, we are going to move on now to our special guest in just a moment. So when we get back after this quick break, we will have Dr. Matt Greenhouse, project scientist on the James Webb Space Telescope team, to tell us all about it. So we'll see you back here in just a few minutes. Bye. All right, welcome back, everybody. We are here with Dr. Matt Greenhouse from the James Webb Space Telescope team. Thank you so much for joining us this evening.
Thank you for having me.
Yeah, I must say I was shocked when you agreed to do this with us the month that James Webb was scheduled to launch. So, like, even more kudos to you for making this happen for us. We're really excited to have you this evening.
Sure.
So yeah, we've got a bunch of slides up that you shared and some really cool videos to share with everybody. And yeah, I mean, we'd love to just kind of let you take it away. And if our co-stars have any questions, I hope you don't mind if they ask questions. And then we've got our audience listening in, and they might chat some questions as well for you.
Sure. Let's try and leave the questions to the end, but let's get into it.
All right, let's do it. We're all yours.
Sure. So first slide.
It's up there. Yeah, you should be good.
Oh, I don't see the slides. Boy, that's going to be a little weird, but okay. Okay. Well, I'm Matt Greenhouse. Thank you for tuning in to hear about the James Webb Space Telescope project. If you can go to the next slide. There really is no way for me to see what slide you're on, I guess. Is that the case? Or maybe if I turn off
Sorry,
my
Matt,
camera.
if you pin Gavin's video, you should be able to see the overlay.
If I do what to Gavin's video? Okay.
If you pin it in the Zoom window.
I don't know what that means.
Oh.
pin. Okay, I got it now. Okay, great. I'm able to see the slides. All right. Traveling back in time is the stuff of science fiction, but looking back in time is science fact. And space telescopes are our most powerful tools for looking back in time. And this is why we create them. So what do I mean by looking back in time? If you look at a person who is sitting in the room with you right now, you're not seeing them as they are. You're seeing them as they were a few nanoseconds ago. Now, a nanosecond is a really, really, really small amount of time. So we don't perceive that transmission delay. It takes light a few nanoseconds to travel from the person next to you into your eyes. We don't perceive that. But if we look at objects farther and farther away, the finite speed of light makes that transmission delay more pronounced. So for example, if we had a magic switch that would switch off the sun, and we flip that switch, it would be 500 seconds before we knew anything had happened. That's because it takes 500 seconds for light to travel from the sun to the earth. So when we look at the sun, we're not seeing it as it is right now. We're seeing it as it was 500 seconds ago. Similarly, when we look at the closest star, we're seeing it as it was 4 years ago, and so on. And when we look at astronomical objects farther and farther away, we are seeing them as they were farther and farther into the past. And with the JWST, we will look back in time more than 13 billion years. Okay, next chart. All right, so the JWST mission was conceived in the late 1990s to connect the dots, if you will, between the famous image that is shown in the upper left of this slide, which was taken by the COBE satellite. This is an image of the moment in time when the universe became transparent after the Big Bang and light could escape. So the universe was a few 100,000 years old when we're seeing the universe as it was when it was only a few 100,000 years old in this COBE image. The colors in this image denote temperature inhomogeneities. And so these blobs in the image of slightly warmer temperature are the seeds that give rise to galaxy formation. In the lower left of the chart, we have the deepest image that was taken by the Hubble Space Telescope early in its mission, the so-called Hubble Deep Field. And that image shows us what the universe looked like when it was about a billion years old. And between the epoch that COBE observed and the farthest into the past that HST can observe, between these two epochs, there's an epoch of the universe that is very, very poorly observed. It's called the cosmic dark zone. And it's of great scientific interest because it is the point in the evolution of the universe where the first stars and galaxies formed. And the reason that it's poorly observed is we haven't had the right type of telescope in space to see that a moment of the past. And so that was the impetus, the original impetus for the JWST mission. Next chart. Okay, and start the animation on this chart, if you will. All right, now when Hubble took its famous image, it stared at a single spot in the sky for a long, long, long time, leaving the camera shutter open, if you will, for a couple of weeks. And this is what that image revealed. And you can see the image is full of objects. Almost every object in this image is a galaxy. Only a small handful are foreground objects. And you can see that there are lots and lots of very faint red galaxies that are left to see. So Hubble has not looked back to the point of galaxy formation for certain reasons having to do with the design of the Hubble telescope. All right, let's look at the next chart and go ahead and start that animation. Now, when JWST begins its science program this summer, it will do a very similar measurement. It will leave its camera shutter open, if you will, for a long, long, long time, staring at a single spot in the sky. Only JWST can see farther back in time than Hubble. And JWST can see a different spectrum of light than Hubble can see. And so when JWST does this experiment, we will see all the way back to galaxy formation such that there's nothing left to see, with increased exposure. All right, so next chart. All right, now when we say that JWST will see the first galaxies, we don't mean that you will pick up a copy of your local newspaper and see a picture of the first galaxy. What we mean is that is shown on this plot. We will measure the rate of star formation in the universe per unit volume in the universe as a function of look back time, as a function of redshift. And this is what we know today. And one can see that at high redshifts, these data points start to have large error bars, and then the data stops. That's because we don't have JWST. And so with JWST, we will be able to fill in this plot all the way to very high redshift. And we will, at some point, see a precipitous drop-off. That'll be the epoch of galaxy formation. And the data will be of high enough quality so that we can distinguish between various theoretical models of the evolution of the universe. And so that's what we mean by seeing the first galaxies. All right, next chart. All right, now, and start the movie on this chart. Now, in the, not that movie, not that movie either. All right. Yeah. All right. This is a supercomputer simulation of the formation of the universe. And this is what we hope to see in reality with JWST. But in this simulation, one can see that the normal matter in the universe is distributed in a spider web type arrangement called the cosmic web. And where these filaments of the web intersect, you have galaxies. And this is what the structure of the universe looks like today. And how it evolved from the Kobe image to this structure is something that the web will help us understand. All right, let's go back to the chart. Okay, and just hit next to start an animation. Okay, now when we look at galaxies today, they're very symmetric in their shapes. Some have spiral arms, some have bulges, but they're very round, they're very symmetric morphologies or shapes, as they're called. Okay, hit return. Or hit next, Sam. All right, when we look, hit next again too. Oh. There we go. All right, when we look at galaxies in the past, way in the past at high redshift, they don't look this way. They don't have these regular morphologies. They're sort of beaten up, irregular blobs of light, as shown here. So as we look way back in time, what are beautiful symmetric galaxies turn into irregular galaxies. Why? We don't know. But the JWST will help us understand that. We believe that galaxy collisions, which were more common in the past, probably account for this change in morphology. And if you could show that movie of galaxies colliding.
Matt, I think we lost your your
Okay,
video.
well, let's
You want to check that real quick?
We lost my audio or video?
Your video. We can hear you, but we can't see you anymore.
Okay.
There we go.
Okay.
Perfect.
So if you could start that video of galaxies colliding, if you can, not that one. All right, let's just skip it. Let's just skip it and go to the next chart. I'll go actually to the next chart. All right. Now you've all heard that space is expanding. What do we mean by space is expanding? We don't mean that the objects are flying through space as if from an explosion. What we mean is shown in this analogy. What you have here is a loaf of raisin bread dough that's been put out to rise. All right, so up on the top of the chart is showing this raisin bread dough rising. Now imagine that you're sitting on one of the raisins. What would you see? You would see all the other raisins moving away from you, even though you are not at the center of the expansion. And no matter what raisin you chose to sit on, you would see the same thing. This is a pretty good analogy for what we mean by the universe is expanding. We mean that the actual space is expanding. And so when we look at galaxies around us, all the galaxies appear to be moving away from us, but we are not at the center of anything. So now go to the next chart. Not that chart, the one before that one. No, keep going. Go one more, maybe. Here we go. All right. Start this animation, or if you can. All right. When these distant galaxies emit their light, they emit their light in the ultraviolet part of the spectrum. But as that light travels to us through the expanding space, through that expanding raisin bread dough, the wavelength of the light is stretched into the infrared. So to see that light today, we have to build an infrared telescope. That's one of the reasons why the Hubble cannot look back in time to this cosmic dark zone, because it lacks the infrared capability. So in designing the JWST, we've had to build an infrared telescope. All right, now let's go to the next chart. Keep going. I want that spectrum chart. If you could go back, I just wanted to explain what the infrared was. The Cosmos folks are having a lot of technical difficulty here, but let's go back.
Yeah, then go back a couple slides.
Right there. Okay, so what do we mean by infrared light? A light comes in an infinite spectrum of wavelengths. The wavelength can be infinitely long or infinitely short. And our eyes are only sensitive to a very narrow slice of this whole spectrum of light that exists. It's called the electromagnetic spectrum. Only a small portion of it can pass through the Earth's atmosphere and reach the surface. And lucky for us, because a lot of it is harmful. But our eyes have evolved to just be sensitive to that narrow slice. But a lot more light exists. And so the infrared portion of the spectrum is the wavelength of the light is just a little bit longer than our eyes can see. Our skin can feel infrared light, but our eyes can't see it. So if you hold your hand near an electric stove burner, even though the burner is black, you can feel the heat from the burner. What your skin is sensing infrared light from that burner. That's what you feel as heat. If we go a little shorter in wavelength than the visible, we're in the ultraviolet part of the spectrum. Our eyes can't see that, but our skin can be burned by it if you're on the beach too long. All right, so JWST will operate from the red end of the visible out into the mid-infrared. The Hubble operates from the visible a little bit into the ultraviolet. And so that's one of the key differences between JWST and the Hubble. that prevents Hubble from observing the early universe. All right, next chart. Keep going. All right. This is a famous image taken by Hubble of an object called the Eagle Nebula. And next. All right, and let's take a close-up of that. And this is a very famous image called Pillars of Creation, taken by Hubble. You probably all have seen it. Now, what is this image? The spaces between the stars in our galaxy, the so-called interstellar space, is not a cold, empty vacuum. It's filled with dust, it's filled with gas and plasma. It's got a lot of stuff in it. And it has giant clouds of molecular gas, and that's what's shown here. These pillars are pieces of a cloud of molecular gas, and there's a lot of dust mixed in with that gas. And so it appears opaque in this visible light image. And these molecular clouds are of great scientific interest because this is where stars are born. These clouds collapse on themselves due to self-gravity. And as the cloud collapses on itself, the pressure inside the cloud gets very, very high. And that causes the temperature inside the cloud to get very, very high. The situation is very similar to filling your bicycle tire at a gas station. When you fill your tire up, the tire gets a little bit warm. Same thing happens inside these clouds, only inside these clouds, it gets really, really, really warm to the point where nuclear fusion can occur. And this is how stars are formed. All right, now let's go next. All right, if we look at that same image in the infrared part of the spectrum, one can see that the infrared light can see through the dust and allow us to study the star formation in a much more effective way. And so the infrared capability that we put into the Webb telescope to see the early universe is crucially important for doing lots of other science that has nothing to do with understanding the first stars and galaxies. And like Hubble, the JWST will do a wide range of science, and much of it is enabled by its infrared capability. All right, let's go to the next chart. All right, now when stars form, there is typically a disk of leftover material that surrounds the newly formed star. And these circumstellar debris disks, as they're called, are of great scientific interest because this is where solar systems, planetary systems like our own, form. And they form from these disks. There's a movie on the slide. Why don't you go ahead and show it? Now, this is a computer animation of one of these circumstellar disks. And you can see that something is happening to the disk in this movie. The disk is being sculpted into bands. And that sculpting is the result of planets that are orbiting the star and sweeping up material in the disk. So now if you go back, stop the movie and go back to the chart. This is a radio telescope imagery of many of these sculpted debris disks taken with a large radio telescope in Chile. And one can see that by observing the sculpted nature of these disks, we can tell that planets are there without even being able to see the planet. JWST will do a lot of this kind of work, and it's a crucial way for us to study planets around other stars and detect their presence. All right, let's go to the next chart. All right, in the upper left of this chart, one sees an artist's rendition of the debris disks surrounding our own star, the sun, alongside a map of that actual debris. This debris, these chunks of rock and ice, are the so-called Kuiper belt objects or trans-Newtonian objects. And they exist in the outer regions of our solar system. And this is of great interest because this debris is pristine leftover primordial debris from the formation of our solar system. So of course, we want to study that. And so that is an objective of the JWST. And we have put special tracking capability, non-sidereal tracking, into the JWST to allow it to observe these Kuiper Belt objects, comets, and the planets of our own solar system. So go ahead and next. All right, and go one more next. Well, go back. All right, just leave it here. We recently visited a Kuiper Belt object for the very first time. In 2014, the New Horizons mission that we sent to fly by Pluto, after we flew by Pluto, we sent it on to this Kuiper Belt object. And this is what we saw. It was very exciting. It turned out to be two objects stuck together. And this has been computer modeled to be the result of a very low velocity collision. It's been shown that when objects like this collide at a few kilometers per second, they can stick without either one being destroyed. And this is of great interest for planetary formation theory, in which planets are formed by agglomeration of small particles over time to produce planets. And so JWST will be studying the Kuiper Belt, and it should be fantastic. All right, next chart. All right, JWST will also study the planets of our own solar system. JWST will study Jupiter's Great Red Spot. This is a storm that's been raging on Jupiter for more than 400 years. It seems to be shrinking, and JWST will help us explore why the red spot is red. We still don't know why it's red. The Webb will search for small moons of Saturn that are too faint for flyby spacecraft to have seen. And one of the most exciting things that the Webb will do in the solar system is to study moons of Saturn and Jupiter. Enceladus and Europa are believed to have vast oceans covered by a thick crust of ice. And these oceans can harbor life, similar to life that we know exists on the mid-Atlantic ridge of the Earth, independent of the sun. And as tidal forces act on this thick crust of ice that's covering these oceans, there are cracks and geysers erupt. And shown on the lower right of this slide is an actual picture of this ejecta taken by the Cassini spacecraft. And so JWST will be studying the chemistry of the ejecta from these geysers to determine what the composition of this ocean is and to look for as evidence of life. It should be very exciting. All right, next chart. Next. All right. Now, when I was a graduate student, there were no planets known outside our solar system. Today, we believe that all stars have planets, and there are, I don't know, between 4,000 and 5,000 planets known. So the implication is that there are tens of billions of habitable worlds in our galaxy. That doesn't mean they're inhabited, but there are a huge number of habitable worlds. And we have learned how to search for life on them. And so the search for extraterrestrial life is no longer the stuff of science fiction. It is a major science objective of NASA. And let's talk about how it works. Next chart. All right. So how can we search for life on a planet that is so far away that it's just a dot of light? And the answer is that we will do this by studying the atmospheres of the planets with a method called spectroscopy. In spectroscopy, we can spread light out into its component colors so that we can see the emission from individual atoms in molecules in the object that's producing the light. And So we can produce a spectrum, and we can actually identify which atom and molecule is producing the light that we're seeing. So here in the upper right, we have the Earth, Moon, and Venus, and a spectrum of their atmosphere. So a spectrum is just a plot with brightness on the y-axis and wavelength on the x-axis. And you can see that, say, the spectrum of the Earth's atmosphere, for example, has all these bumps and wiggles. Every one of those bumps and wiggles is due to an atom or a molecule absorbing or emitting light, and we can identify which atoms and molecules are doing that. If the Earth had no atmosphere, the spectrum would just be a flat line. So by recording a spectrum of the exoplanet atmosphere, we can determine its chemistry and look for chemistry that can only result from biological processes. Well, how do we get this spectrum? We will use a technique it's called transit spectroscopy, and it works like this. A significant fraction of exoplanet solar systems are oriented so that the planets orbit along our line of sight. So in this little cartoon picture we have here, imagine that we have our telescope. So this prism is our telescope. We're looking at a star, and imagine that there's a planet orbiting that star that happens to be along our line of sight. And we take a spectrum. What will we get? We will get a spectrum of the star plus a spectrum of the planet's atmosphere. Now, if we just wait a little while for the planet to move out of the way and take the spectrum again, we have a spectrum of just the star. We subtract the two, voila, you have a spectrum of the planet's atmosphere. And this has been turned into an exact science with Hubble, and this is done a lot now, and this will be a major activity for JWST to understand the chemistry of exoplanet atmospheres to search for life. Let's go to the next chart. All right, so when we first put pencil to paper on what did we need to build to do all that science, we realized that we had two enormous problems. One was that we needed 7 times the light gathering capacity of the Hubble Space Telescope. And we needed Hubble's ability to see fine detail, angular resolution, as they call it, but at the longer wavelength where JWST will be working. And that also requires a large mirror. And this mirror that we needed was bigger in diameter than the biggest rocket. So that was problem number one. Problem number two was that to build an infrared telescope, the telescope has to be made very, very cold, almost minus 400 degrees Fahrenheit. Why? Because anything above absolute zero emits light. And so if we didn't make the JWST super cold, it would be blinded by its own infrared emission. The JWST is about 6.5 metric tons. And then and now, there was no refrigerator powerful enough to cool something so big to this low temperature. So those two problems in the mid-90s really stumped us, but we did solve them. So let's take a look at how we solved them. Next chart. All right, so how did we solve the cooling problem? To solve the cooling problem, we determined that we would not put the JWST in orbit about the Earth. Rather, we will put it in orbit about a special spot in space called the second Lagrange point of the Sun-Earth system. That's a big mouthful. We just call it the L2 point for short. So this is shown on the right side of this chart. And the thing that makes the L2 point special is that you can see that all the sources of heat on the JWST, the sun, the Earth, and the moon, always lie in the same direction when we're at the L2 point. So we determined that if we deploy a giant sun shield, the size of a tennis court, so that the telescope would live in the shadow of this sun shield, it will cool passively to the cold darkness of space and reach its desired temperature without any kind of refrigerator. So as long as we keep the JWST in the shadow of its sun shield, it will reach the desired temperature. Now, the JWST has to point all over the sky to be useful to us. And so how does it do that and still stay in the shadow of its sun shield? Well, you can see that we've designed the sun shield so that we can observe an arc on the sky 50 degrees long, and the sun will not peek over the front or the back of the sun shield. And now you can see that if we rotate the JWST about the Earth-Sun line, that won't spoil our shadow situation at all. And so now that arc turns into an annulus that covers 35% of the sky. So at 35%, so at any instant in time, JWST can observe 35% of the sky and always be in the shadow of its sun shield. Now, as the Earth orbits the sun, the L2 point orbits the sun with the Earth. And so now we're rotating about this, we're rotating about that north ecliptic vertical axis in the figure. And so now you can see that that annulus will sweep over the sky every 6 months. So every 6 months, JWST can observe any spot on the sky and still be in the shadow of its sun shield. Now, we're not putting the JWST precisely at the L2 point, but rather we're putting it in a small orbit about the L2 point. And the reason for that is with JWST, we're generating electricity with solar rays. It takes about 2 kilowatts of power to run the web. And so it's important that we keep it out of the Earth's shadow. And so that's why we're in an orbit about the L2 point. All right, let's go to the next chart. All right, how did we solve that mirror problem? We adopted something called a segmented mirror architecture. Instead of building a single big mirror, we built 18 hexagonal segments that could play together as if they were part of a single mirror. And that allows us to fold the telescope up inside the 5-meter fairing of the Ariane 5 rocket that we're using as shown here. This rocket will launch from French Guiana, which is on the east coast of South America. And it will launch from a place called Kourou Launch Center in French Guiana. And the unfolding of this observatory is what you'll see in the next video. That origami involves 40 deployable structures and 178 release mechanisms, all of which have to work perfectly. The astronauts cannot go to the L2 point to fix this if it doesn't work, so we have to get it right. All right, next chart, or show the next chart and show the animation. There you go, show that. All right, so the first thing that happens is the solar rays come out. We're operating on batteries up to this point. There are some rocket firings that get us on course to the L2 point. The JWST will not orbit the Earth even once. The high gain antenna comes out so that we could begin communicating with the JWST. And now you see these giant pallet structures unfolding. And inside those pallet structures is folded up the giant sunshade that we spoke of just a moment ago. All right, now you see a telescoping boom separate the telescope from the pink stuff that you see there. That's to provide thermal separation between what will be a super cold telescope and what must remain a room temperature spacecraft. And now you see these telescopic booms pulling the sunshade out of those pallet structures. And these spreader bars at the end separate the sunshade into its 5 layers. A trim tab comes out to help us trim what is a big solar sail. Various other radiators and deployments occur. And soon you'll see the telescope itself unfold. So there's the secondary mirror of the telescope unfolding, and the wings of the primary mirror unfold much like a round drop leaf kitchen table. Okay, and there you have it. Next chart. All right, the JWST mirrors that you just saw there are not made of glass like most telescope mirrors. They're made of beryllium. And beryllium's a metal Why did we choose beryllium? As this telescope slews across the sky, even though it's in the shadow of its sun shield, there are small temperature gradients that will form inside the mirror. So we had to find a material that was super light, super strong, and had a low coefficient of expansion, thermal expansion, at this very low operating temperature of almost minus 400 Fahrenheit. Turns out beryllium has that property. And so the beryllium is mined in a powder form. It's compressed under tremendous heat and pressure into a block of material. And after we go through all the trouble to do that, you could see in this figure that we machine away almost all the beryllium to make a very, very lightweight mirror segment. The figure of merit here is areal density, mass per unit area. And in that metric, the Webb mirrors are about 6 times lighter than the Hubble mirrors, and they're the current state of the art for lightweight mirrors. All right, next chart. All right, go ahead and start this animation. This is a robotic pick and place machine that we designed, and this is in a clean room at Goddard. And this machine has a robotic arm with a high precision tool on the end of it that is allowing helping the technicians mount the flight mirrors on the telescope structure. What you're seeing here are the actual flight mirrors. They look black because they have covers on them to keep them clean. Okay, but you get the idea of how this was done. Okay, next chart. All right, let's talk about that sunshade a little bit. The JWST sunshade has an SPF of 1,000,000. So if you had this on the beach, you would be very, very well protected. It is literally the size of a tennis court, 73 by 40 feet. It has 5 layers. Each layer is made with a heat-resistant plastic material called Kapton that is thinner than a human hair. The sunward-facing layer is coated with silicon, so it actually looks pink in reality. And all the other layers are coated with aluminum to give it that SPF of 1,000,000. The sunshade has a special curved shape to ensure that stray light can't reflect off it and get into the telescope. And to make a curved shape out of flat cloth, those of you who sew know that you have to have lots of seams. And so each layer of this sunshade is a quilt of about 50 pieces with 7,000 inches of high precision seaming. It's not done with needle and thread, but instead with thermal spot welds. But this sun shield is was one of the hardest things to develop in the JWST mission, and it's one of the highest risk areas of the mission. But all this work is behind us now. Okay, let's go to the next chart. And go ahead and start this animation. All right, and so this is just a test of folding up that sun shield inside that pallet structure you saw. These plastic tables on each side are there for gravity offloading, so they're not there in space. But this is just an example of some testing, the kinds of testing that have to be done. You'll notice there's a person appearing in the center of the sunshade, and that gives you a sense of scale, how big this thing is. And if you look closely, you can actually see the quilting and so forth. Okay, and you can see the 5 layers. Okay, let's go to the next one. All right. So after we got the Webb telescope all put together and the science instruments put on it, we put the Webb in a special shipping container, a very special shipping container that's truck mounted, that keeps the JWST preserved in the super clean special environment that it needs to be in. And we designed this to integrate with the C5 aircraft, so that we could roll this container right into the aircraft. It just barely fits, as you can tell, but we did get it in there. And we flew it from Andrews Air Force Base to Houston, Texas, to do what is called an end-to-end optical test. Let's go take next chart. All right. Now, to do this test, we needed to find the biggest cryo space simulation chamber in the world. And we did find that left over from the Apollo program at Johnson Space Flight Center. It's called Chamber A. And this is on the left, on the right, rather, you can see a picture of looking through the door of Chamber A, and there's the Apollo command module in there. We pulled this chamber out of mothballs and refurbished it for the JWST mission so that we can put the whole JWST telescope, as shown on the left, into this space simulation chamber and observe special optics test equipment in the top of the chamber and do this in the environment that JWST, simulated environment that JWST will operate in. So this chamber simulates the vacuum of space and the coldness of space. And this end-to-end optical test, the test is just the mental image that you form when I say end-to-end optical test is exactly the right image. We're going to shine light right through the whole system and make sure that everything is working. This is a test that we skipped on the Hubble Space Telescope program with consequences that you're probably aware of. But because the astronauts cannot fix this observatory, we did not skip this test on JWST. It's a very difficult, expensive test to do. And it was lucky we didn't skip it because we did find some problems. But that test is all behind us now. Let's go to the next chart. All right, so then after we finished that test, we went back into the aircraft and we flew from Houston, Texas to Los Angeles, California, where our contractor, Northrop Grumman Aerospace Systems, can add the spacecraft and the sun shield to the assembly. Let's go to the next chart. Okay, so I think there's a movie, so let's go ahead and show this movie. And the movie does have sound. But this is a picture of the JWST telescope in the stowed configuration being mated to the sun shield and the spacecraft. You can't really see it's underneath the sun shield at Northrop Grumman. And so this is the first time that the whole JWST mission came together. And of course, when we assemble it, we have to test it. All right, now after we got this integration done, we're not done yet. We have to now take this whole level of assembly and put it on a vibration to simulate the vibration that it will experience during the rocket flight to space. And then we have to put it in front of giant loudspeakers and blast it with acoustic energy to simulate the sound that the JWST will experience in the rocket flight to space. And then we have to test the whole thing to make sure that it really works. All that work is behind us now. Let's go to the next chart. All right, so with the completion of all that, now the payload is too big to put in the aircraft. So instead, we expanded the shipping container and then went on to a roll-on, roll-off transport ship. And we shipped out of Seal Beach, California, which is near Long Beach, California, went through the Panama Canal to French Guiana, so just a few weeks ago. And then we roll off the ship at the launch facility in French Guiana. This is the first time that NASA has transported a payload to the launch site by ship. But this work is all behind us now. We're there. So let's go to the next chart. All right, let's show this movie.
This is your telescope, an engineering marvel.
And I hope you're hearing sound.
An exploration powerhouse.
Okay, good.
Use it to look back in time and explore the first galaxies that formed after the Big Bang. To peer into atmospheres of planets orbiting the stars. It's your eyepiece to the uncharted, unknown, and unimagined. This is the largest, most complex, and challenging space telescope ever constructed. It will change our understanding of the universe and our place in it. The James Webb Space Telescope. with the largest primary mirror ever to be flown in space. At 6.5 meters, it's more than 6 times the size of the Hubble Space Telescope primary mirror. Webb's 4 cutting-edge infrared instruments and cameras operate at super cold temperatures. Temperatures colder than the surface of Pluto. Getting this cold is done with the help of the largest sun shield ever flown. A 5-layer, tennis court-sized sun shield that blocks heat from the sun, Earth, and moon. Webb will be the first telescope to detect light from the most distant galaxies in the universe. These first galaxies formed about 13.5 billion years ago, only 300 or so million years after the Big Bang. Webb carries advanced technologies to tackle some of the most fundamental questions about the universe. How did the first galaxies form and evolve? Are there chemical signatures of the building blocks of life on other worlds? Is our solar system unique? Launching such a large telescope into space is an incredible engineering challenge. Fully deployed, Webb is too large to fit inside any rocket fairing. Engineers designed it to be folded, like origami, to squeeze inside the European Space Agency's 5-meter diameter Ariane 5 rocket fairing. After launch, controllers on the ground deploy Webb remotely. Deployment is an intricate ballet. For nearly 3 weeks, controllers carefully unfold Webb. After this delicate dance, Webb's golden mirrors are precisely aligned using motors behind each hexagonal mirror segment, adjusting them to form one perfect mirror. Once the instruments are fully cooled, the exploration will begin. Webb is a technological challenge like no other, born of the efforts of thousands of people across the United States, Canada, and Europe. The James Webb Space Telescope is your telescope. Use it to explore, to challenge theories, to see sights yet unseen. It's yours to unfold the beauty and mystery in the universe and our place in it.
All right, let's go to the next chart. All right, so the questions that drive NASA astrophysics: how does the universe work? How did we get here? What are we evolving into? You know, is there life in the universe? The Webb mission will enable our next step in humanity's quest for answers. I'm sure the Webb will like Hubble, will raise more questions, as many questions, you know, as it answers. Next chart. So if you're in the audience of the Cosmos Show, you can join the quest for answers. The people that do projects like this come from all walks of life, all backgrounds. Projects like this involve scientists, engineers, managers, accountants, even lawyers. And they come from all backgrounds. And you can be one of them. There's a quote that I like to read. The book of nature lies continuously open before our eyes, but it can't be understood without first learning to understand the language and characters in which it is written. It is written in mathematical language, and its characters are geometrical figures. That's as true today as it was 400 years ago when Galileo said it. So to work in this field, to have a career in aerospace, to grow up to design spaceships, that's something you can really do. And to do it, just go to college. Study what you love, but if that includes science, engineering, and math, stick with it. And this is a real career option for you if it strikes your fancy. The most important thing to do in planning your career is to make sure you're doing something that you love, because most of your life will be spent at work. And so it's important that you study what you love. But if this is what you love, it's not unrealistic to think in these terms for a career objective. Go to college If you're there already, stay there and study what you love, and just have the confidence to jump into fields like this. All right, thank you. Thank you for having me. Go to the next chart. Those were my remarks for tonight, and you can follow the action on the JWST launch that's coming up in about 15 days at NASA Web, #JWST, and #NASAWeb. Our website will be a great place to follow the action. And of course, you can watch the launch on NASA TV and hear a lot of interesting commentary. And I'll answer any questions for as long as you have them.
All right. Well, Matt, thanks so much. That was awesome. Really appreciate it. We already have one question, not specifically about the James Webb Space Telescope, but an interesting question specifically for us who call ourselves amateur astronomers. The listener wants to know when you think amateur astronomers are going to get adaptive optics.
You have to talk to Celestron or somebody like that. You know, it probably will happen. I mean, it won't be cheap, but well, I don't know, because you're not going to have the lasers that are used by ground-based telescopes are, dangerous lasers. So you're not going to get one of those. But yeah, I think it'll be a while actually before you have truly adaptive optics.
Yeah, I'm not holding my breath either, but I think you're right. I think someday it'll come. I had a comment about something that you said earlier, which I absolutely love. So I lead stargazing programs all the time. And when I'm telling people about what it's going to be like on the Earth once the sun enters its red giant phase and later its planetary nebula phase, I tell them that if they're not wearing a million SPF, it's going to be a really bad day. Always thinking that that's just some like hypothetical thing that's never going to happen. How did I could have possibly known the James Webb Telescope can actually supply that million SPF for them? Yeah. I love that. Now we just need a few billion copies of it.
Sure.
Any of the co-stars have any questions for Matt?
I was curious on a kind of historical note of the differences in James Webb Space Telescope and Spitzer, and why Spitzer wouldn't be able to look at the dark ages.
Yeah, Spitzer was very small, and it basically is much too small to have the sensitivity to see what we're aiming to see. And it also has no, very low angular resolution, again, because it's so small. Yeah.
I was wondering about the lifetime of JWST. Correct me if I'm wrong, but so kind of Hubble, we've gotten like way more bang for our buck than we ever hoped, and hopefully we'll continue to. But with the fuel supply on James Webb is 10 years. Is that like a hard stop? Like there's just no chance that we're going to get any extra life out of it?
Yeah, great question. So that little orbit about the L2 point that I mentioned, we're trying to stay out of the Earth's shadow, that orbit is unstable. And so it needs to be maintained with station-keeping thrusters. And so we have the propellant for those station-keeping thrusters tanked up to last at least 10 years. Now, it could last much longer. It will depend on how efficient we are at using the observatory. And our operations center is the Space Telescope Science Institute. They have a lot of experience operating Hubble. So they're very good at operating, observatories efficiently. And so I suspect it will last longer than 10 years. But there is, unlike Hubble, there is a finite lifetime to this mission. When that fuel is exhausted, then JWST will fall out of that orbit about the L2 point into some general sun-centered orbit, and then the mission will be over.
Will it eventually like run into the sun, or is it just going to be floating out there?
It'll just be left
dead,
dead in a sun-centered orbit. Yeah.
Wow, that is going to be one piece of space junk.
Right.
On a question about the a little bit more on the instrument in the science case. You covered it. Obviously, it's got a huge breadth, but which one's your favorite? Do you have a favorite instrument and a favorite science case?
Well, I don't have a favorite instrument because I was responsible for them all, so I love them all. It's like asking somebody if you have a favorite kid, but
everyone has a favorite kid.
I was going to say there's usually a real answer to that.
But there are amazing instrumentation that in each one it redefines the state of the art. I mean, the near cam instrument, the main near infrared imager, has an enormous detector complement compared to anything we've done before. Superb image quality. It does coronography and a little bit of GRISM spectroscopy. The near spec instrument is a remarkable instrument. It's the first true multi-object spectrometer to fly in space. It can target 100 objects simultaneously and keep the spectra separate. And the reason we did that is because those faint primeval galaxies, they're so faint that if we had to observe them one at a time, we would never get a sufficient sample size. And the MIRI instrument does imagery, spectroscopy, coronography. It's a very powerful instrument. And even the fine guidance sensor has a science mode that's geared toward exoplanet spectroscopy, the so-called NIRIS instrument. So we are covering the waterfront. There are integral field units with the integral field unit of the near spec and the MIRI. One can obtain an integral field spectrum over the entire wavelength operating range of JWST. And so real powerful stuff. And it should be as impactful as Hubble was. I mean, the Webb will literally give humanity its first high definition view of the infrared universe.
And what about a specific science case you're really excited about?
Oh, the science case. Well, I mean, like everyone else, I'm excited about exoplanets. I really am. I mean, the prospect of finding, finding even a plausible case for life would be transformational. And, the actual discovery of life will take multiple missions and lots of bio indicators. But JWST will really begin that process, and it should be very exciting.
Do you have a prediction on when that discovery will be announced?
Oh, I don't know. It really will take multiple missions because it's not enough to just see a few biomarkers. You have to work out the chemistry of the atmosphere. And then as many of you know who are on this call, the process of science, it takes a lot of data and time and analysis to build the consensus in the science community that something like discovery of life requires.
Yeah, definitely. We've got a few more minutes. We've got another question from one of our viewers. The question was, and maybe an interesting one here, why was the redshift infrared of expanding space not relevant to previous telescopes in the way it is to the James Webb Space Telescope?
Yeah, well, it is relevant. It's always there, and it was relevant to other facilities. But the other telescopes, they can't look as far back in time as the Webb. And it's really when one is trying to see the early universe that this really comes into play. But it's there all the time. The looking back in time is there all the time, and it affects every mission that we do.
So is that just because the Webb has a larger collecting area, so it's seeing?
Yes, two things. The Webb has a larger collecting area. It has the ability to see the correct part of the spectrum. Mm-hmm. And with that larger collecting area, it has this both two things that the collecting area gives us. The large collecting area gives us sensitivity, and the large diameter of the mirror gives us angular resolution. Lambda over D, because we're operating in the infrared, lambda is getting bigger, so D has to get bigger to have the same lambda over D as Hubble has. And that ability to see fine details is also very important, along with sensitivity.
Kind of on that note, and a historical question, when we, I guess, first launched or conceived of Hubble, did we know that it wasn't going to be able to see the earliest galaxies?
Yeah. Oh, yeah. Well, let's see. What did we know back in those days? We certainly knew that it would not see.
I mean, we knew the Big Bang and the expansion rate and so forth. So presumably, but then I guess I'm not sure we knew enough about when Hubble was launched about like the history of galaxy evolution and when that would have started off.
We've learned a lot since Hubble was launched, but there was no surprise about what Hubble's capabilities were.
Well, initially,
except the lack thereof early on.
Except that little snafu in the beginning. Yeah.
All right, we're just about out of time here, Matt. I want to bring you back to that question I mentioned before we went live about we've been working on this project for a couple of decades now, and as you mentioned, lots of people have asked you lots of questions. But what's the one thing that you wished everyone or someone would have asked you about your work over the past couple of decades that nobody's asked?
Well, I think in terms of the web, the emphasis is always about the sensitivity of the observatory, but the angular resolution is really, really, really important to the science capability. And so, I try and remind people that is a driver for the large mirror as much as the sensitivity is. If we don't have the ability to see fine detail, we won't be able to, meet the science objective. So, that's one thing I kind of bring up. But I've spent my whole career, on this thing. I joined the web in '97, and, now we're finally launching it. So it's been a really, really long journey, but boy, it's been transformational to me as a person and as a scientist and so forth. So I encourage people really to get involved with projects like this, because it's a wonderful thing, and it's a rare honor and opportunity to work on these things.
Just a quick question, just so I can feel like I'm in with the cool kids. Is that what you call it around the office? The web?
The web, yeah.
All right, excellent, thanks.
So I'm sure you're going to be sleeping very soundly on December 22nd.
Oh yeah.
after all these years.
Yep.
I can't even imagine the anticipation that you're feeling, Matt, after all this time, and we're talking about like days away.
Yep. Yeah, about 15 days away. So it's going to be fantastic, and will really be a new era for astronomy.
Well, I hope you have plans for a really big party. We're having a launch party actually at the Wyoming Stargazing office as well. So
excellent.
We'll definitely be thinking about you. Well, thanks again for being here. We've got a gift for you for helping us out, and so our operations director Maggie will get in touch with you about that. Just a token of appreciation, and appreciation to everyone who's out there watching the Cosmos show tonight. We wouldn't be here without all of you, as well as to all of our co-stars. Thank you all so much for being here and sharing your enthusiasm about space exploration. And to all the folks behind the scenes on Wyoming Stargazing, and especially our stream master Gavin and everybody else who makes this show possible. I'm really excited to be here with you. So thanks so much. And we'll see you again in a couple of weeks. Until then, be well, and don't forget to look up. We'll see you next time.
Bye-bye.
Bye.